Every year, governments around the world invest hundreds of billions of dollars into mega projects, massive bridges, high-speed railways, artificial islands, mega airports, entire new cities. These extraordinary projects are designed to reshape economies, create millions of jobs, and improve the lives of future generations. Some of them become engineering masterpieces admired around the world. Others become symbols of innovation and national pride. But not every mega project ends in success. Some consume billions of dollars before construction is even halfway complete. Others open years behind schedule. Some never achieve the goals they were originally designed for. And a few are abandoned entirely, leaving behind unfinished structures, empty construction sites, and difficult questions about how so much money could produce so little value. So what causes these enormous projects to fail? Is it poor engineering? Unexpected geological conditions? Political decisions? Financial problems? Or is the reality much more complicated? The truth is that mega projects are among the most difficult undertakings humans have ever attempted. Unlike ordinary buildings, these projects often take 10, 15, or even 20 years to complete. During that time, governments change, economic conditions shift, material prices rise, technologies evolve, environmental regulations become stricter, even population forecasts can change dramatically. A project that seemed perfectly planned on paper can face completely different challenges by the time construction is underway. Engineering itself is rarely the only obstacle. Modern megaprojects require thousands of contractors, hundreds of suppliers, and tens of thousands of workers to operate in perfect coordination. A delay in one area can trigger a chain reaction across the entire project. A single design modification may require months of additional engineering. Unexpected ground conditions can force foundations to be completely redesigned. Global events can disrupt supply chains, delaying critical equipment for months or even years. As the schedule slips, costs continue to rise. Public expectations increase. Political pressure grows. And every new delay attracts even greater media attention. Yet, despite these challenges, governments continue investing in mega projects. Why? Because when they succeed, the rewards can be extraordinary. A new railway can transform regional economies. A bridge can connect communities that were once separated for generations. A modern airport can become an international gateway for millions of travelers. A hydroelectric dam can provide clean electricity for decades. The potential benefits are enormous, but so are the risks. Throughout history, some of the world's most ambitious construction projects have become powerful lessons in planning, management, engineering, and decision-making. Some failed because their goals were unrealistic. Some struggled because the world changed faster than the project itself. And some simply became far more expensive than anyone could have imagined. Today, we're taking a closer look at several of the world's most controversial megaprojects. Projects that promise to change the future, but instead spark debates about cost, delays, and whether the investment was truly worthwhile. More importantly, we'll explore what engineers, planners, and governments learn from these experiences. Because every unsuccessful project leaves behind something valuable: knowledge. And sometimes, those lessons become the foundation for building something even greater. Our journey begins in the United States, where one of the most ambitious transportation projects in modern history set out to revolutionize travel, but quickly became one of the most debated infrastructure projects ever undertaken. Let's begin with the California high-speed rail. In 2008, California voters approved one of the most ambitious transportation projects in American history. The vision was bold: a modern high-speed railway stretching across California, eventually connecting San Francisco and Los Angeles, with trains traveling at speeds of more than 200 miles per hour. Supporters believed it would transform transportation across the state. Travel times would be dramatically reduced. Traffic congestion on highways would decrease. Air travel between major cities could become less necessary. And millions of passengers would have access to a cleaner, faster, and more sustainable way to travel. At first, the proposal appeared achievable. Early estimates placed the cost at around $33 billion. Construction was expected to move steadily over the following years. But as engineers moved from concept drawings to real construction, the complexity of the project became impossible to ignore. California is one of the most geographically and environmentally diverse regions in the United States. The railway would need to cross mountain ranges, fertile farmland, densely populated cities, active earthquake zones, rivers, highways, and existing rail networks. Every kilometer introduced new engineering challenges. Bridges had to span major highways without disrupting traffic. Viaducts were designed to cross flood-prone areas. Hundreds of utility lines required relocation. Land acquisition became another enormous obstacle. Unlike building through undeveloped desert, much of the planned route passed near privately owned farmland and established communities. Negotiations, legal disputes, and environmental reviews often took years before construction could continue. At the same time, engineers faced increasingly strict environmental requirements, protecting wildlife habitats, maintaining water resources, reducing noise, and minimizing impacts on local communities all required additional planning and design revisions. Each modification improved the project in one way, but also increased both cost and construction time. Then came another unexpected challenge: inflation. The global rise in material prices dramatically increased the cost of steel, concrete, fuel, and heavy equipment. Labor shortages affected construction schedules. Supply chain disruptions delayed the delivery of specialized components. Every delay placed additional pressure on an already enormous budget. Today, the California high-speed rail project remains one of the most debated infrastructure investments in the United States. Supporters argue that projects of this scale always require patience. They point to other major rail systems around the world that also face years of construction before becoming essential parts of national transportation networks. Critics, however, question whether the original budget and timeline were ever realistic. They argue that repeated cost increases and schedule changes have undermined public confidence. Despite the debate, construction has never completely stopped. Across California's Central Valley, workers continue building bridges, viaducts, earthworks, and railway infrastructure. Every completed section represents years of engineering effort involving thousands of workers and countless technical decisions. Whether the project ultimately fulfills its original vision remains a subject of ongoing public discussion. But one lesson is already clear: building a high-speed railway is not simply about laying tracks. It requires balancing engineering, environmental protection, politics, finance, and public expectations over many years. When any one of those elements changes, the entire project must adapt. And sometimes, that adaptation becomes almost as challenging as the engineering itself. California's railway is only one example. Our next project faced an even greater challenge: an airport designed to become one of Europe's most advanced transportation hubs, yet delayed for years by a cascade of technical and management problems that few people saw coming. Let's travel to Germany and examine the remarkable story of Berlin-Brandenburg Airport. In the heart of Europe, Germany set out to build an airport that would represent efficiency, precision, and world-class engineering. Berlin-Brandenburg Airport, known simply as BER, was expected to replace the city's aging airports with a single, modern aviation hub capable of serving millions of passengers every year. The project appeared straightforward. Germany had one of the strongest engineering reputations in the world. The technology already existed. The funding had been approved. Construction moved forward with confidence. At first, everything seemed to be progressing according to plan. Runways were completed. Terminal buildings began taking shape. Massive steel structures rose across the construction site. Glass facades reflected the growing skyline. From the outside, the airport looked almost ready to welcome its first passengers. But beneath the surface, serious problems were beginning to emerge. One of the biggest challenges involved the airport's fire protection and smoke extraction systems. Modern airports are incredibly complex buildings. In the event of a fire, smoke, not flames, is often the greatest danger. Engineers must ensure that smoke can be controlled, extracted, and kept away from evacuation routes long enough for passengers to leave the building safely. At BER, this system became one of the project's greatest obstacles. As construction progressed, repeated testing identified issues that required redesigns, additional installation work, and further inspections. Each change affected other parts of the building. Electrical systems had to be modified. Control software required updates. Mechanical equipment needed further integration. What appeared to be a single technical issue gradually expanded into a much larger coordination challenge. At the same time, the project faced another invisible problem: complexity. An airport is not simply one building. It is a network of thousands of interconnected systems: lighting, security, baggage handling, escalators, elevators, ventilation, communication, emergency power, fire protection, passenger information displays. Every one of these systems must work together seamlessly before an airport can open. If one critical system fails certification, the entire facility must wait. As delays accumulated, costs continued to rise. Construction teams remained on site far longer than originally planned. Additional inspections became necessary. Previously completed work sometimes required modification to accommodate new requirements. Public attention intensified. Media outlets closely followed every announcement. Questions grew louder. How could one of Europe's most anticipated infrastructure projects experience so many delays? The answer was not a single catastrophic mistake. Instead, it was the combined effect of numerous technical challenges, project management decisions, evolving requirements, and the difficulty of coordinating one of the most complex public construction projects in Germany's history. Eventually, after years of additional work, testing, and certification, Berlin-Brandenburg Airport finally opened to passengers. But by then, it had become much more than a transportation project. It had become a powerful reminder that even countries with exceptional engineering expertise can struggle when project complexity outpaces coordination. BER demonstrated an important lesson for engineers around the world. Building impressive structures is only one part of a megaproject. Successfully integrating thousands of independent systems into one reliable operation can be an even greater challenge. As technology becomes more advanced, megaprojects become more intelligent, but they also become more complicated. And sometimes, managing that complexity becomes the hardest engineering task of all. The next project would present an entirely different challenge. It wasn't an airport or a railway. It was a stadium built to inspire a nation. Yet it spent decades carrying the reputation of being one of the most expensive and controversial sporting venues ever constructed. Let's examine the remarkable story of Montreal Olympic Stadium. When Montreal won the right to host the 1976 Summer Olympics, Canada saw an opportunity to introduce the world to a bold new architectural landmark. At the center of that vision stood the Montreal Olympic Stadium. Its design was unlike almost anything built before. A massive elliptical structure, a soaring inclined tower, an ambitious retractable roof. It wasn't meant to be just another sports venue. It was designed to become an international symbol of innovation and modern engineering. But turning that vision into reality proved far more difficult than anyone had expected. Construction began in the early 1970s under an extremely demanding schedule. The opening ceremony of the Olympic Games could not be delayed. Every day mattered. Every week counted. As engineers pushed to meet the deadline, the project became increasingly complicated. The stadium's unusual architecture required construction techniques that were considered highly advanced for the time. Its signature inclined tower was one of the most ambitious structural elements ever attempted on a sports stadium. Building such a complex structure demanded extraordinary precision. At the same time, labor disputes, design revisions, and rising construction costs created additional pressure. Delays became increasingly difficult to avoid. Budget estimates continued to climb. Project schedules became tighter. Engineers were forced to balance quality, safety, and time under enormous public scrutiny. When the Olympic Games finally opened in 1976, the stadium was still incomplete. Some planned features had not yet been finished. The famous retractable roof, one of the stadium's defining characteristics, would require years of additional work before becoming operational. Even after completion, technical challenges continued. The roof system underwent multiple modifications over the following decades as engineers searched for long-term solutions to improve reliability and performance. Meanwhile, the project's financial impact became one of the most discussed aspects of its legacy. Construction costs had increased dramatically compared with the original estimates. For years, the stadium became widely associated with budget overruns and long-term public debt. Some critics even nicknamed it the Big O, a play on its official nickname, the Big O, referring to the financial burden created by the project. Yet the story does not end there. Despite its difficult beginning, the stadium has continued serving the public for decades. It has hosted sporting events, concerts, exhibitions, and millions of visitors from around the world. Its distinctive silhouette has become one of Montreal's most recognizable landmarks. What once symbolized controversy eventually became part of the city's identity. The Montreal Olympic Stadium reminds engineers of an important lesson. Innovation always carries risk. The more ambitious a design becomes, the greater the importance of realistic planning, accurate budgeting, and effective project management. Extraordinary architecture can inspire generations, but without careful coordination between design, construction, finance, and execution, even the boldest vision can become far more expensive than anyone originally imagined. As remarkable as Montreal's story may be, the next project would challenge not just engineers, but the very idea of how future cities could be built. A project so ambitious that it continues to divide opinions around the world. The line, footage dam des soit to Hodam, concrete pouring, steel erection, tower cranes, curved steel structures, large stadium-like construction, heavy lifting, night construction, drone time-lapse. Few megaprojects in modern history have captured global attention quite like the line. When Saudi Arabia first unveiled the project, it immediately became one of the most ambitious urban development plans ever proposed. Instead of expanding cities outward, the line would grow upward. A perfectly linear city stretching for approximately 170 kilometers through the desert. No traditional streets, no private cars, high-speed transportation connecting one end to the other in just minutes. Powered increasingly by renewable energy and designed around walkable neighborhoods, the project promised to redefine how future cities could function. For many people, it sounded like science fiction. For engineers, it represented one of the greatest construction challenges ever attempted. Building a conventional city is already incredibly complex. Building a city unlike anything ever built before is something entirely different. Construction began with enormous earth-moving operations across the Saudi desert. Thousands of workers, hundreds of excavators, massive drilling equipment, concrete plants operating around the clock. Entire logistics networks were established to support continuous construction in one of the world's harshest environments. Satellite images soon revealed just how quickly work was progressing. Excavation corridors stretched across the landscape. Construction camps expanded. Heavy equipment operated day and night. To many observers, it looked as though one of history's greatest engineering projects was finally becoming reality. Then questions began to emerge. Media reports highlighted changes to project timelines and development priorities. Some reports suggested that certain phases of the project would be adjusted as planning evolved. At the same time, the scale of the investment drew worldwide attention. Developing entirely new infrastructure in the desert requires far more than constructing buildings. Roads, power generation, water supply, telecommunication, waste management, underground utilities, public transportation. Every essential service must be built almost from scratch before millions of future residents can even be considered. This dramatically increases both cost and complexity. Like many megaprojects, the line must also balance engineering ambition with financial planning, construction logistics, workforce availability, and long-term economic goals. Projects of this scale rarely follow a perfectly straight path. They evolve. Designs change. Construction priorities shift. Budgets are reviewed. Schedules are updated. That reality is common across many of the world's largest infrastructure developments. Despite the ongoing debate, construction has not simply disappeared. Work continues across multiple parts of the broader NEOM development, while plans for the line continue to evolve over time. Exactly how the project will look when completed remains one of the biggest questions in modern engineering. Supporters argue that every revolutionary project appears impossible until it is finished. Critics believe the scale, cost, and timeline remain extraordinarily challenging. Both perspectives highlight an important truth. History often judges megaprojects only after decades have passed. Many projects that were once criticized eventually became symbols of engineering excellence. Others never achieved the vision originally promised. Today, the line remains somewhere between those two possibilities. Not a completed success, not a confirmed failure, but perhaps the world's largest engineering experiment currently under construction. Whatever its final outcome may be, the line is already changing how engineers, architects, and governments think about the cities of tomorrow. And perhaps that is its greatest achievement so far. But after examining these remarkable projects, one question remains. What can engineers around the world actually learn from them? That lesson may be far more valuable than the billions of dollars invested. Let's conclude with the engineering principles that determine whether a mega project succeeds or struggles under its own ambition. After examining these extraordinary mega projects, one question remains: were these projects truly failures? Or were they simply the unavoidable cost of pushing engineering beyond anything humanity had attempted before? History rarely provides simple answers. Many of today's greatest engineering achievements were once criticized for being too expensive, too risky, or too ambitious. The Channel Tunnel connecting Britain and France faced years of financial uncertainty before becoming one of Europe's most important transportation links. Large hydroelectric dams around the world were often questioned during construction, yet today they provide reliable electricity to millions of homes. Even some of the world's busiest airports and longest bridges experienced years of delays before becoming essential pieces of national infrastructure. Mega projects are different from ordinary construction. They are not built for next year. They are built for the next 50 or even 100 years. That long-term vision makes planning incredibly difficult. No engineer can perfectly predict future economic conditions. No government can guarantee political stability for decades. Technology evolves. Construction methods improve. Material prices fluctuate. Population growth changes. Climate conditions become increasingly unpredictable. Every mega project must adapt to a future that no one can fully foresee. Perhaps that is why the most successful projects are not always those with the biggest budgets. They are the projects capable of adapting when reality changes. Flexibility, strong leadership, transparent decision-making, careful engineering, and realistic expectations. These qualities often determine success far more than concrete, steel, or machinery alone. The projects we've explored today each faced different challenges. California high-speed rail demonstrated how large infrastructure must balance engineering with environmental, legal, and financial realities. Berlin-Brandenburg Airport reminded the world that integrating thousands of complex systems can be even more difficult than constructing the building itself. Montreal Olympic Stadium showed how bold architecture must always be supported by disciplined project management. And the line continues to test the limits of what modern engineering, technology, and urban planning can accomplish together. Some of these projects may ultimately exceed expectations. Others may never fully achieve the vision first presented to the world. Only time will deliver the final verdict. But one thing is already certain. Every one of these mega projects is expanding the knowledge of future engineers. Every challenge solved today becomes experience for tomorrow's builders. Every mistake becomes a lesson that can prevent even greater problems in the future. That is how engineering has always progressed. Not through perfection, but through continuous improvement. As our cities continue to grow, as populations expand, and as humanity tackles even greater challenges, the next generation of megaprojects will demand ideas that seem impossible today. Some will succeed, some will struggle, and some will completely change the future. If there's one lesson history continues to teach us, it's that every extraordinary achievement begins with someone willing to attempt what others believe cannot be done. Thank you for joining us as we explored some of the world's most controversial megaprojects. If you enjoy discovering the stories behind groundbreaking engineering, massive construction projects, and the technologies shaping tomorrow's world, subscribe to Anthill's BuildVerse, because the next impossible project may already be under construction.